Well, in the next, we will show that finally our learning process has a risk that is finite, even we are going to learn in an infinite family of hypotheses. We started our journey from using Hofstad's inequality to limit the risk of bad evaluation, of poor evaluation for a single hypothesis. And then we discuss how about to extend this discussion to the learning process rather than a single hypothesis. We immediately find we encounter a difficulty that we are learning a mostly infinite number of hypotheses, so there is no direct generalization is available. So we then use the relationship to transform the format of the risk from the difference between the in-sample evaluation and the out of sample, which is the generalization risk error, to compare the in-sample evaluation on two independent hypotheses, two independent data sets. And we calculated the risk of having such independent risk is a limited number. But if we try to extend the same using the same way to the hypothesis family, which is infinite, we encounter the same kind of problem. Well, starting from here, we find there is a fundamental advantage of comparing two in-sample errors than to compare the in-sample error and out-of-sample error. The point is, this difference between two independent in-sample errors, the difference is affected by only by the behavior of a hypothesis on 2n training samples. So any behavior, any whatever kind of weird behavior of a hypothesis out of the 2n, the two independent data sets, is irrelevant. Say if these are the 2n samples, we have a hypothesis which gives us the prediction of the samples on the samples in this way. So whatever how correct or how they are errors of those predictions, if we consider the in-sample error of one data set and between one data set and another, note this illustration illustrates the behavior of this linear hypothesis on the 2n data set. This is not to see on one side there is one data set, on the other side there is another data set. And probably maybe data set 1 contains this point, this point, this point, this point, this point, maybe this point, and the data set 2 contains other points. So if we compare the behavior of this hypothesis on the two data sets, I think it would be a better idea to mark the two data sets. Well, now I have marked the membership of the training samples belonging to two independent data sets, dataset 1 and dataset 2. For example, if the error measured on dataset 1, let us call that A in, and that measured on dataset 2, let us call that E in prime. So the point is here, For this hypothesis, we have some difference measured between E in and E in prime. But consider one of its fellow hypothesis in the linear family. The important thing is, although those two hypotheses are different in the family, but when we only concerned with their behaviors on those two n data samples, the A in and A in prime, the difference between these two independently assessed in-sample errors, the difference are the same for the two hypotheses. And also you can see the difference actually could be the same for infinitely many linear hypotheses. Therefore, in this way, we would be able to greatly reduce the multiplication factor here. Actually, we can reduce it by an infinite factor, so much so that we only consider all possible different binary classification results on the two endpoints. We call them dichotomies. Only the number of dichotomies on the two endpoints generated by the family that counts. So the largest possible number of the dichotomies is 2 to the power of 2n. Of course, if we exhaustively color all those two endpoints into two different ways, if we exhaust all the combinations, we can have 2 to the power of 2n, this many dichotomies. This is, of course, not so great, but this is a huge step from the infinitely many hypothesis members. Now, we have transformed the multiplier of the risk from the number of members in the hypothesis family into the different ways of how those members in the hypothesis family behave on a limited sample set. So now we will have our risk in this way. Please note that the factor 2 is not what we will use finally, because to constrain the probability of in-sample error and out-of-sample error, we need to enlarge. We need to multiply this bound by another 2. So finally, we will need to multiply another 2. But this is of no concern here. We multiply, the important part is instead of multiplying the size of the hypothesis set, we change that into 2 to the power of 2n. However, soon we will find that if we stop here, this is a nice looking bound, but it's of no use. The reason is that the mathematical power we are given by the bound is that we know that this bound decreases exponentially with respect to n. Look, the n is on the power of the exponential term, and it is a negative term. So when n increases, the risk will decrease exponentially. But unfortunately, now we give it a multiplier which increases exponentially, although the bases are different. One is the natural base, and the other is a natural exponential base. The other is 2. But they compares with each other. So the multipliers increase exponentially with n, and the other factor, the risk of individual hypotheses, decreases exponentially with n. When we put these two factors together, we do not have any kind of guarantee. So, is learning doomed here? Well, fortunately, we do not necessarily have this exhaustive capacity for all hypothesis family. Consider the linear hypothesis family. You are probably be able to create some linear hypothesis to separate the samples in this way. Or if you do not happy with, if the samples change, the training samples that, okay, we need to separate the two classes in this way. They are both tunable within the linear hypothesis family. But if the hypothesis, the training samples tells us that the different classes on the data space distributed in this way, then there will be no linear hypothesis could generate this kind of classification of two samples. This is beyond the capacity of the linear hypothesis family. It is just this limitation, just the incapable of generating whatever kind of dichotomies that might be presented by the training samples. This limitation itself limits the total capacity of the hypothesis, limits the number of behaviors, number of dichotomies that could be generated on the 2n samples. This limitation gives us the hope that finally the risk of the learning process could be limited. Very maybe the minimalist example. Say our hypothesis family is really limited. We can only generate, if the binary classification problem is defined on one-dimensional data, we have only one x, and the hypothesis function is a step function, so it sets a threshold, and whatever x below the threshold would be classified as negative, and whatever is beyond above the threshold will be classified as positive. We represent two classes using green and red color. So if we apply this hypothesis family on 2n equals 4 data samples, we can exhaustively list all possible dichotomies. Sorry, I need to remove this. All possible dichotomies that could be generated by this hypothesis family. They go this way. So if we put the threshold wherever below this point, we will have the all positive classification. If we move the threshold between this sample and this sample, we will have this classification, so on and so forth. Although there are continuously infinitely many members in this hypothesis family, because you can change the threshold to whatever value you want, whatever real value you want. But there are only 5 possible outcomes if we apply this entire family on 4 data samples. So it is not difficult to calculate that the most dichotomies for this hypothesis family on 2n samples is 2n plus 1. Then we can convert this exhaustive number of 2 to the power of 2n into 2n plus 1, as here. Instead of we are considering 2 to the power of 4 equals 16 possible coloring or classification schemes on the 4 data samples, we need to only consider 2n plus 1 equals 5 possibilities. If we substitute this 2n plus 1 into the bound, we will have equation like this. And this will be finally limited by the power of exponential trend. So here I draw a graph of this. Although it seems that for some quite number of the samples, the threshold is of no use. Look, it's more than 200, nearly 300. For some probabilities, it's of no use. But eventually, it will drop below 1 into some meaningful threshold. And this trend goes forever into when we increase the number of n. So in the next, we will consider a powerful limitation, a powerful way of limiting the number of possible hypotheses, dichotomies a hypothesis family could generate on some limited number of training samples. So we'll discuss this term. We will establish that we'll have some polynomial term here. Although the polynomial could be passively large, so that it seems that we need some close number of training samples, but this is a theoretical guard, which means in theory we are guaranteed when we have large n, the exponential term will prevail and we will have some meaningful limit of the generalization risk of the learning process.